Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will see next part of groups. Let us see theorem. Normalizer, that is centralizer of an element A belongs to G is a subgroup of G. Normalizer, that is centralizer of an element A belongs to G is a subgroup of G. You know the definition of normalizer or centralizer. That is normalizer NA equal to set of all X belongs to G, where G is a group, such that AX equal to XA. This theorem statement is normalizer, that is centralizer of an element A belongs to G is a subgroup of G. Consider the proof of this theorem. Let A belongs to G be arbitrary element. You know that AE equal to EA, where E is an identity element. This implies E belongs to NA, since it satisfies the property AE equal to EA. Now consider x comma y belongs to NA, so that this implies XA equal to AX and YA equal to AY by definition of normalizer or centralizer of an element. Now AX equal to XA implies by multiplying both sides on left by X inverse, we get X inverse AX equal to X inverse XA. That means multiplying equation AX equal to XA on both sides by X inverse on left, we get this term. This implies X inverse AX equal to, on the RHS side we get EA, since X inverse into X equal to E, and this implies X inverse AX X inverse equal to A into X inverse. This term comes after multiplying the previous term by X inverse on both sides on right side. That is the term X inverse AX equal to EA. That means X inverse AX equal to A, since EA equal to A. Multiply this term on both sides by X inverse, so that we get X inverse AX X inverse equal to EA, that is A into X inverse. This implies X inverse into A into E. E means X into X inverse equal to E, equal to RHS side as it is, which is equal to A into X inverse. This implies X inverse into A, since AE equal to A, which is equal to RHS side as it is, which is equal to A into X inverse. This implies X inverse belongs to NA, since NA means set of all. You know that set definition of centralizer or normalizer, that is set of NA equal to set of all X belongs to G such that AX equal to XA. In such manner, we get here the term X inverse into A equal to A into X inverse, so that X inverse belongs to NA. Now consider the term X into Y inverse in bracket, multiply by it by A, which is equal to X into in bracket Y inverse into A bracket complete, and this term equal to X in bracket A into Y inverse bracket complete equal to XA in bracket XA bracket complete into Y inverse equal to in bracket AX bracket complete into Y inverse equal to A into bracket xy inverse bracket complete. Here only the commutative associative property is used, that is xy inverse into a equal to x into y inverse into a, which is equal to x into ay inverse, that is commutative property is used. Commutative property means definition of centralizer or normalizer is used. Thus, since in normalizer we get ax equal to xa, so that y inverse into a equal to a into y inverse. Thus, x comma y belongs to NA implies xy inverse belongs to NA. Hence, NA is a subgroup of G. Let us consider one example. Let G equal to set plus minus 1 comma plus minus I comma plus minus j comma plus minus k be a group of quaternions. Find the normalizer of each element of G and verify that they are subgroup of G. We have to find the normalizer of each element of G and we have to verify that they are subgroup of G. Consider the solution. Here n1 equal to n of minus 1 equal to G. Ni equal to n of minus I equal to plus set plus minus 1 plus minus I. Here consider first step, n1 equal to n minus 1 equal to G. That means multiplying each element of G by 1, we get the group G as it is. That means set of all elements of group G, hence it is equal to G. Also multiplying by minus 1 to all elements of group G, we get all elements of group G, hence it is equal to G. Thus we get first step. Now consider second step, Ni equal to n minus I equal to set plus minus 1 comma plus minus I. That means Ni, consider Ni equal to set on the RHS side plus minus 1 plus minus I. That is multiplying the set on RHS side by I, we get I into 1 is I into minus 1 is minus I into I is 1 minus 1, I into minus 1 is plus 1. That means we get the set on RHS side. Also multiplying by minus I to the set on RHS side, we get the set plus minus 1 comma plus minus I. Similarly, Nj equal to n minus j equal to in bracket plus minus 1 comma plus minus j, and Nk equal to n in bracket minus k bracket complete equal to set plus minus 1 comma plus minus k. Now consider another theorem. Statement of this theorem is intersection of subgroup of group G is a subgroup of G. That means we have to prove that intersection of subgroup of a group G is a subgroup of G. Consider proof of this theorem. First we prove that intersection of two subgroups of a group G is a subgroup. Let H1 comma H2 be two subgroup of group G. Then X comma Y belongs to H1 intersection H2 implies X comma Y belongs to H1 and X comma Y belongs to H2. This implies XY inverse belongs to H1 and XY inverse belongs to H2. by previous theorem. This implies xy inverse belongs to H1 intersection H2. Hence, H1 intersection H2 is a subgroup of group G. Now we have to prove that intersection of HI is a subgroup of G. Now consider second part. Let set HI, I belongs to capital I, be a family of subgroup of group G. Then x comma y belongs to intersection of HI, I belongs to I. This implies x comma y belongs to HI for all I belongs to capital I. This implies xy inverse belongs to HI for all I belongs to I by previously discussed theorems. This implies xy inverse belongs to intersection of HI, I belongs to capital I. Hence, intersection of HI, I belongs to I, is a subgroup of group G. Thus, we have proved the theorem. Now consider one remark. Union of two subgroups need not be a subgroup. That means union of two subgroups is a subgroup. The statement is not true always. Now we consider one example of it. Consider example. Let H1 and H2 be two subgroups of group Z, plus, defined by H1 equal to set dash 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 comma minus 6 comma minus 3 comma 0 comma 3 comma 6 comma dash 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 bracket complete, and H2 equal to, H2 is another set which is equal to set dash 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 comma minus 10 comma minus 5 comma 0 comma 5 comma 10 comma dash 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 bracket complete. Here we have assumed that H1 and H2 be two subgroups of group set is Z, plus. Z is set of integers and binary operation is plus. Here H1 and H2 are two different sets. Then H1 union H2 equal to set dash 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 minus 10 comma minus 9 comma minus 6 comma minus 5 comma minus 3 comma 0 comma 3 comma 5 comma 6 comma 9 comma 10 comma dash 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 bracket complete. But this set H1 union H2 is not a subgroup of Z. Also, H1 intersection H2 equal to set dash 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 comma minus 30 comma minus 15 comma 0 comma 15 comma 30 comma dash 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 set complete. Note that H1 intersection H2 is a subgroup of Z. Now, if H3 equal to, consider another sets, H3 equal to set dash 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 comma minus 4 comma minus 2 comma 0 comma 2 comma 4 comma dash 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 bracket complete, and another set H4 equal to set dash 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 comma minus 8 comma minus 4 comma 0 comma 4 comma 8 comma dash 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 bracket complete. Then H3 union H4 equal to set dash 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 comma minus 6 comma minus 4 comma minus 2 comma 0 comma 2 comma 4 comma 6 comma dash 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 bracket complete is a subgroup of Z. This is because set H4 is subset of H3. Thus, we have seen that union of two subgroups need not be a subgroup. That means the statement is not true always. In some cases it is a subgroup and in some cases it is not a subgroup. Also, previously we have seen that one theorem intersection of subgroups of a group G is a subgroup of G. Thus, we have proved the theorems and solved the examples. Thank you.